to the cloud. So we're going to find the maximum minimum values of this function on the interval of 0 to 5. Now, a good strategy before you even get started, and this is one of the reasons why we reviewed piecewise functions, is to graph this function over the given interval, right? So f of x, is equal to, we have 2x plus 5 over 3. I could put the fraction in first, 2x plus 5 over 3. I could also have simplified a little bit. And in fact, when we go to take the derivative, that's in fact what we're going to do. But then open the squiggly bracket and then put in your interval here. Remember, this is interval notation, but this corresponds to 0 is less than or equal to x, which is less than or equal to 5. All right. So 0 less than or equal to x, less than or equal to 5. So we're only concerned with this piece. Now, you could also, I mean, if you didn't want to do it that way, you could have also just graphed the whole function and ignore anything that's beyond 0 and 5. You know, that would have been okay too. So what we're looking for when we say the absolute extrema are the highest and lowest y values over this interval. I mean, it's pretty obvious, I think, that the lowest y value is right down here. The highest y value is right up here. So graphically, we already have the answer. We want to learn how to do this analytically because, one, it's not always going to be as simple as a linear function, and two, it's not always going to be as simple as a two-dimensional function. You know, like when you go further in your explorations of math, you're going to find that you're not just limited to 2 dimensions, you know, and you want to be prepared for it. So I'm going to rewrite this function, f of x. I'm going to write it as 2/3 x plus 5/3. Finding the critical numbers, critical values. We talked about this last time. That just means finding the derivative. In this case, 2/3. Then take that derivative and set it equal to 0 or set it equal to undefined. All right, undefined as in 1 over 0. All right, so set f prime of x equal to 0 and f prime of x equal to 1 over 0. The issue with this problem is that there's no x in my derivative. So we're not going to get a solution out of that. All right. If there is no solution, you know, I could do it. You know, I could say 2/3 equals 0. Well, that's not true. 2/3 equals undefined, also not true. So what that tells me is that there are no critical values. Critical values, critical numbers, remember I talked about this last time, means the same thing. All right, we go back and forth and calling them one as opposed to the other, so we talk about them interchangeably. All right. So there's no critical numbers. Because there's no critical numbers, critical values, all we would have to do is find f of a, f of b. Now our interval contains endpoints. Those endpoints, first one is the a value, the second one is the b value. So this is saying find f of a, which in this case would be f of 0. Find f of b, which in this case would be f of 5. Whichever one is the biggest out of these two possibilities is going to be the absolute maximum. Whichever one is the smallest is going to be the absolute minimum. Now you could plug it into the original function, or you could just evaluate it by hand. By Desmos is what I meant to say. Pop in f of 0. Pop in f of 5. All right. So 1.6 repeated is going to be 1 and 2/3 or 5/3. F of 5 gives us a 5. So this would be our absolute minimum, and this one would be our absolute maximum. All right. So what we want to do, as we very often do, is make a Desmos that's going to work more often than not. Let's just put it that way. Because, you know, like, honestly, I mean, I like to think that I can build a Desmos that's going to work in every single case, but I'm sure there's probably something I'm not considering. But if we make it as general as possible, it's gonna help, you know, at a minimum. So what we can do first off is make our bounds as general as possible. So instead of 0 and 5, let's make that A and B and create sliders there. Okay, so now I have bounds for my function. So depending on where I put my A value, I'll get a different start to the line, and where I put my B value, I'll get a different end to the line. So in this case, I wanted 0 and I wanted 5. All right. Now, instead of saying f of 0, I would say f of A. Instead of saying f of 5, I would say f of B. All right, what this would give us is the y values of the endpoints. All right, and like I always do, or I'll always intend to do, I'll jazz this up and put it up on Blackboard later, but you now have a method by which you can determine the values, the y values of the endpoints on an interval. All right, all you would have to do is adjust what we put in here. So for example, in the second one, number 13, for some reason, I can't remember. I would imagine, yeah, number 11, okay. So I would put in x squared plus 2x minus 4. This is over the interval of -2 to 1. So the x value is -2, the y value is a 1. Overshot the 1. So now I have the relevant piece of the quadratic. Now, these are clean numbers, so you can actually just look at the picture. But I actually have the relevant piece. I could determine visually what my extreme values are. But I now know that f of A, which is f of -2, is going to be a -4. My f of B, which is the same as f of 1, is going to be a -1. So now I just have to do the calculus to verify that the turning point right here gives a y value that's lower than the endpoints give. Because it looks like I already have my absolute max. My absolute max seems to be at -1. All right, we can call that at this point. But the differentiation process, f prime of x, will give us the analytic result showing the critical number corresponding to that turning point, which it should in turn give us the absolute minimum. All right, but we'll see. All right, so f prime of x would be 2x plus 2. We're going to set f prime of x equal to 0. We're going to set it equal to 1 over 0. So 2x plus 2 equals 0. 2x plus 2 could actually never be equal to 1 over 0. You try to solve that, you're not going to get a solution. So we're not worried about this piece. But the other piece, subtract the 2. You get 2x equals -2, making x equal to -1. This is the CV, also known as the critical value. All right, so what we do to find the absolute extrema is we just pop that in. All right, our critical value gets plugged in, x equals -1, gets plugged into the original function, and we just take note of what the corresponding y value is. Now we just look at the graph, or we could plug it in if you want, or you could even write f of -1 here. Either way, you're going to get a -5. The biggest number out of this set is your absolute maximum. The smallest number out of these possibilities, and only these possibilities, would be your absolute minimum. All right, and I'll show you in a minute how you could generalize the substitution of the critical value. So the question is, why are critical numbers important, and or what do we do? Well, if we find them when the derivative is equal to 0 or undefined. Critical points occur at turning points. All right. So if there's a turning point in a graph, it must occur at a critical value. All right. So a turning point could be, if we just go back to this dreadful diagram, any one of these turnaround points here, 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 and also here. Any one of those, they would correspond to critical values. Those critical values are instances in which the derivative is either equal to 0 or 1 over 0. Right? So just by identifying the instance in which the derivative is equal to 0 or undefined, just like we did with these graphs here, you know, if we have a nice continuous function, just by identifying the turning point, we can identify the corresponding critical value. But analytically, we tend to want to go the other way, where we're not even looking at the graph. We look at whatever the critical value is, knowing that that's most likely going to be a turning point. We can use that to evaluate. In every single case here, we had a turning point corresponding with either 0 or undefined. All right, so we know that if we wanted to go the other way, we just look for instances in which the derivative is either 0 or undefined, and that checks out. All right, good question. So number 12. Oh, number 12 doesn't have a critical value because our derivative doesn't have an x in it. So when I go to set it equal to 0, there's no way to actually solve for an x that isn't there. Right, so there's got to be an x in your function in order for it to be equal to 0, because 2/3 could never be equal to 0. It's a contradiction. It could never be equal to undefined. Same deal. Also, good question. Mm-hmm. So, looking at number 14, maximum value. So same deal, except now you can see things are getting a little bit more complicated. Right? It's not going to be as simple as just a linear quadratic function, but we can still take the same approach or a similar approach. You pop in your function, take a look at it over the given domain. So x cubed minus 12x. All right. So x cubed minus 12x over the interval of 0 to 4. So let me make this a 0. Come on. Stay. Said stay. Okay. I'm going to resort to typing it in a sec. All right. And then the other one is 4. All right. So this is the relevant part of the cubic. So in terms of the width, you know, it's a little on the narrow side. So I'm going to adjust my domain here. Instead of going from like -17 to 20, I'm going to go from like -5 to 5. You get a nicer view of the graph. All right. So just by looking at it, we already know where the highest and lowest points are. I get the highest point up here at 16. The lowest point down here, it looks like -16. I can just tap on it. All right. So we kind of know what we're up against going in. So I'd find f of 0. Oops, that's a highlighter. It looked cool, but it's not what I wanted. F of 0. And this one is not difficult to crunch out manually, but it's nice to have the technology do it. F of 4 gives us the result of 16. All right, you see those values right here. All right, that -1 is irrelevant, but I'm going to hang on to that for a sec. I wanted to show you more, I guess, elaborate's not the right word, but If you wanted to use Desmos to actually find the critical values, there's a way to do it. It's just a little bit more tappy, like tapping on the screen rather than command, inputting certain commands. All right, but let me show you the analytic approach first. So f prime of x is going to be equal to 3x squared minus 12. We're going to set that equal to 0, and we're going to set it equal to 1 over 0. And you start to learn that in some cases, the 1 over 0 is not relevant, right? It happens often enough that you start realizing, oh, wait, I can just kind of sort of ignore that step in a lot of cases, because like a polynomial function is never going to be undefined, no matter what you put in for the value of x. If it's a real number, it's not going to be undefined. So you don't even have to bother. But the other one, we solve, factor out of 3, x squared minus 4 equals 0. Set each factor equal to 0, 3 times x minus 2, x plus 2. And you get your critical values of x equals 2 and negative 2. So we test out those values there. So f of negative 2, I'll do first, f of positive 2. So these two numbers, 0 and 4, come from the domain. These two numbers come from the critical values. All right. So then what we would do is we would pop these values into Desmos. We got a negative 2 gives us undefined because it's not in the domain, not undefined because it's a bad value. So negative 2 actually, even though it does give us a number, it's irrelevant because it's not between, I'll just kind of move it here. It's not a value between 0 and 4. All right. And that has to do with the domain restriction. So then I pop in a positive 2 and I get a negative 16. So if I'm just looking for the biggest and the smallest, this is the biggest out of my set. So that's my absolute max. This is my smallest, so that's my absolute minimum. All right. So that, that can be a little on the tricky side just because of that domain consideration, but.
So I have a question.
Yeah.
So those four functions are going to give you like a full scope of the maximum and minimum values of the polynomial?
Correct. If it's not one of these, then it's there's something wrong with the problem because it has to be one of these.
Got it. Thank you.
No problem. So let me just show you real quick. I'm going to get rid of this for a sec. The calculator can graph the derivative function for us. When you type in the original function f of x, it knows that anytime you refer to an f, you're referring to this function. So if we type in f prime of x, so a little up arrow here, like go from lowercase to uppercase. Right next to that enter symbol is the prime. Well, it's apostrophe, but that's what we used. On your keyboard, you would just use an apostrophe. All right, f prime of x, and then hit enter. And what it does is it graphs. In this case, you can see it's only graphing the relevant part of the function, which is good because that's all we care about. All right. Now, what I would want is any value where this function is equal to 0 or this function is undefined. So that's why I was saying that this approach is a little more on the tappy side, right? But what you can do is you can create a new slider. The issue with this is it's going to give you a value, or I don't want to say that. It may give you a value that is only an approximation of what the critical value is, but it may get you going in the right direction. Here, we knew that the critical value was going to be 2 because that's where the turning point was. the derivative needs to be either equal to 0 or undefined in order to have a critical value. So what I could do is I could say f prime of some value c and create a slider for that c value. All right. And like I said, I'll clean this up in a minute. Well, in a minute meaning an hour and a half. But I'll clean it up. I'll save it now, but I'll clean it up later. But if I slide my slider over my interval of a to b, so I would adjust my bounds here to go from a to b. All right, so I'm restricted between 0 and 4 in this case. If I change my a and b values, then I'd be restricted to whatever my new a and b values are. What I would look for is a change in sign. All right, going from negative to positive. So if I'm looking at it, just taking a quick glance, I would see here that around 2, it goes from having negative values to having positive values. And in fact, it might be better to just swap these two. All right. So you see it goes from having negative derivative values to positive derivative values. And at 2, the derivative is equal to 0. All right. So that tells me that my critical value should be equal to 2. Now, there could be more than one, as we've discovered. All right. We've also discovered that even though there's more than one, they may not all be relevant. All right. So that's the case in number 14, but you'll see in a minute when we get to number 16. Well, maybe not even 16, but you'll see in a little bit that they do become very relevant. All right. Or multiple ones become very relevant. So then all you'd have to do, if you really wanted to use this approach in its entirety, is evaluate f of a, f of b, and any f of c or any c value in the function. The key ingredient is that you have to toggle the c value, that slider, to whatever the critical value is, right? At a minimum, and let me see, let me save this as absolute extrema. All right. So if at a bare minimum, you could do all the work by hand here. I'm pointing, it's weird. I'm pointing at the screen as if anybody could see what I'm doing. You can, yeah, I don't know what I do sometimes. You could do all the work by hand and then just use this to do the computations for you if you want. But the C represents the critical value. So I'm going to make a little note of that in here so I don't forget to put it in. Note, let C be a critical value. And I'll just save that. All right. So worst case scenario, even if you don't use this to discover the derivative functions, the critical values, you can do it all on paper and then just slide your slider and it'll give you all the relevant numbers. All right. So that might be something for you. It all depends. All right. So depends on how you use it, but you would be looking for this f of c to either be equal to 0 or 1, or f prime of c to be equal to 0 or 1 over 0. All right. Look for any instance. I type instantaneous more frequently than instance. Instance where f prime of x is 0 or undefined, undefeated, undefined. And now I'll officially save that. I'll still jazz it up a little later, but that's something for you. All right. So the next one, maximum minimum values of the cube root of x over the interval. So my interval is -1 to 1. x to the 1/3 power is the way I would write it. All right. And that's honestly because if there is a cube root function in here, I don't know where it is. So I'm looking at the world's tiniest graph here, not really useful for me. So let me go back to the standard zoom. Probably want to bring it in a lot. All right. So if it gets too confusing to look at the multiple graphs at the same time, just turn one of them off, maybe turn the derivative off. All right. This is what our function would look like. Right. I'm not seeing any turning points. I am seeing a clear maximum and a clear minimum, but we can investigate the derivative part of it anyway. Right. So g prime of x, and again, this is the same. This is the same as saying x to the 1/3 power. G prime of x would be 1/3 x to the negative 2/3. All right. I would rewrite that as 1/3 x to the 2/3, because our next step involves us setting it equal to 0 and setting it equal to 1/0. All right, so 1/3x to the 2/3, it's set equal to 0. 1/3x to the 2/3, I'd set equal to 1/0. Cross multiply. Now that 0 can be thought of as 0/1. I could just introduce that 1. Hey, really 0/anything, but the most convenient way to write it is 0/1. Cross multiply and you get 0 equals 1. That's a contradiction, and so therefore no solution for that. All right, so this is an instance where you don't get a derivative value equal to 0. You do get one where it's equal to undefined. All right, so cross multiply, you get 3x to the 2/3 is equal to 0. The only way that would happen, I mean, you can do all the algebra, but the only way that would happen is if x is equal to 0. All right, and so that's our critical value. All right, so our derivative is undefined at x equals 0. So now we go through the evaluation process. All right, so I could turn my derivative function back on and actually just look at that. It doesn't look like it ever crosses the x-axis. So there's no instance where we would have a function that's equal to 0, but or derivative function equal to 0. But if we're looking for an instance where the function is undefined, scrolling along, 0 gives you an instance where it's undefined. There's never an instance where the derivative is equal to 0. All right. Never an instance where it's equal to 0, but there is an instance where it's equal to undefined. All right. So that gives us a critical value. So I'd set this onto 0 if it stays. Stay. Not staying. And so I look at my values here, and I see we have f of -1, f of +1, those are my endpoints. And then I would evaluate my critical value, f of 0. F of 0 has a value of also 0. So -1 gives a -1. +1 gives a +1. 0 gives a 0. Right? Doesn't always play out that way where you evaluate a function at an x value and it gives the same result as the y value, but it does in this case. You verify it on the graph. And so this would be my absolute minimum. And this is my absolute maximum. Okay. But then the moment you've all been waiting for, the scary looking trig problem. Right? But It's the same approach. There is a part where you'd have to figure out what the derivative of secant is, right? But that's memorization at this point, because we did that in the last unit, all right? So you want to know your derivative rules. It goes a long way. For those of you who don't know, the derivative of secant of x is secant of x times tangent of x. All right. So I would pop in secant of x. My Desmos froze for a second. All right, so under trig, I grab my secant function, secant of x over a to b. Now my a value is negative pi over 6, so I'm going to pop that in there. All right, I lose my slider functionality when I put an irrational number in, but that's okay. I don't plan on moving it anyway. All right, pi over 3. So this is the relevant part of the graph. I would need my c value, again, to be either undefined, to give a result that's undefined in the derivative, or equal to 0. All right, so we'll do it again analytically first, and then we'll look in the calculator. But when it comes to trig problems, you may want to adjust your step to go in trigonometric increments. All right, pi over 12 is a good value to put in. All right, so if you put in pi over 12, it'll count off in pi over 12 increments, starting with the low bound and going to the high bound. All right. And then it'll label it up on your calculator in terms of those radian measures. All right. But I find that sometimes going to the technology for the trig cases, sometimes they're more trouble than they're worth. But or sometimes it is more trouble than it's worth, but it is manageable, right? If that's the route that you want to take. All right, so I need to set my function, my derivative function equal to 0, secant of x tangent of x is equal to 0, secant of x tangent of x is equal to 1 over 0. Something you may want to consider, unless you're an expert at working in terms of secants and tangents, you may want to kick this over in terms of sines and cosines. The secant is the same as 1 over cosine of x. Tangent is the same as sine of x over cosine of x, which in turn would become sine of x over cosine squared of x. So on the left, we'd say it's equal to 0. On the right, we'd say it's equal to 1 over 0. All right, so the computation becomes a little bit more manageable, because now it's just boiling down to your knowledge of the unit circle rather than, more advanced topics in trigonometry. All right, so 0 again could be thought of as 0 over 1. If you cross multiply, you get sine of x is equal to 0. And in the other instance, if you cross multiply, you get cosine squared of x is equal to 0. If you root both sides for this one, you get cosine of x is equal to 0. So now we're just spinning around the unit circle looking for instances in which the sine function is equal to 0. Bearing in mind, we're restricted to a domain of negative pi over 6 to pi over 3. All right. So if I look at a unit circle, I'm just going to do a teensy tiny sketch here. You have 0 and 2 pi. pi over 3 is going to be about right here. A positive pi over 6 would be half of that distance. This is pi over 6. Negative pi over 6 would then be over here. It's just a reflection. All right, so I'm only concerned with this little interval over here of the unit circle. All right, that's all I care about. I don't care about any other part of it. All right, so when I think about that, and I think about where sine is equal to 0, sine is equal to 0 anywhere on the unit circle that's on the x-axis. Cosine is equal to 0 anywhere in the unit circle that's on the y-axis. So this could never be the case, right? Because based off of the diagram I drew, there's never an instance in which that shaded region comes in contact with the y-axis. So I'm only concerned with the first bit. The sine of x equals to 0 on that interval only happens when x is equal to 0. All right, and that's verified by the diagram here. And that's one of the reasons why I'm very keen on getting Desmos involved, because it just goes back to like, what are the minimum requirements to pass a course? You know, like there are people that did just fine in pre-calc, maybe even got an A, but barely know trigonometry. That's not an insult, although it certainly sounds like one. It's just the reality of things. I guess sometimes the reality of things could be an insult. So yeah, maybe it is. Anyway, the point is, what do you do now? You know, like, do you just not know trig the rest of the way? No, you need some way to access this information. And so if you don't know the unit circle, you need some technique that's going to buy you some time until you do. Right? And so this Desmos approach is my suggestion, because you could look at it and say, all right, what am I looking for when I'm trying to find extrema? I'm looking for turning points. Where do I see a turning point? I see a turning point right there at the x value of 0. All right, my derivative graph crosses the x-axis right here, also at 0. So that's consistent, which is a good thing. But even if I didn't notice that, the process here tells me to look for any instance where f prime of x is equal to 0. So I'd slide my c value along until I see a 0 on this interval. It's like, I don't know where it is. Oh, there it is. You know, now that happens when the c value f prime of c is equal to 0. So that means f prime of 0 is equal to 0. All right, over the relevant interval. So we have what we need based off of our analysis in Desmos. You just have to make the analytic stuff jive with that, really. So we have f of negative pi over 6. We have f of pi over 3. And we need f of 0. This is where I realized I've been using f's all along, and some of the problems switched me up and we go to g's and h's. I'd rather actually change the problems and change my work here. So I'll take these as typos. Let's make these f's for forevermore. So we could put the decimal values in. We can also analyze or evaluate the function to get more exact values. But you know, as it turns out, that 1.154 isn't going to be relevant anyway. So it's kind of like, I don't want to say a waste of time, but there's time better spent elsewhere. So 1.155, come on, 2 and 1. Okay, so this is my absolute max, and this is my absolute minimum. All right. Now, in case you're wondering, if you did want to figure out f of pi over 6 by hand, the way you would tackle that sorry, f of negative pi over 6. Secant, as we said, is the same as 1 over cosine. So this would be 1 over cosine of negative pi over 6. Negative pi over 6 is the same as 11 pi over 6. So 1 over cosine of 11 pi over 6. All right, which places it in the fourth quadrant. By ASTC, cosine is positive in the fourth quadrant. So I'm looking for a positive number. All right. So 1 over, now we're looking at a 30-degree reference angle or a pi over 6 reference angle. In our unit circle, and you know, if you don't have access to one right now, you may want to get a hold of one because it's pretty useful to have it on hand. Let me just pull one up. A decent one here. And I found the ones that I completed. That's nice. It's nice to know that Google remembers me. Copy image. Oh, you know what? I realized I'm like a doofus here. I'm using a PC and an iPad, so I can't just move from one to the other. Let me do it on this device. I found a nice one, and then I'm like, you know what? I know what's going to happen here. I'm going to spend the next 10 minutes trying to get it into this device. All right. So let me do this. Fill in filibuster. Fill in the unit circle. Let's see here. Get a nice one. There was one I just found that looked pretty good. Yeah. It's got like straight up handwriting on it, but whatever. Oh, dear Lord. Yeah, after all that, I don't want to read somebody's article. Why can't people do what I do and they just post stuff? Like, here's some math, free math for you. That's what I want. That's all I do. That's all I ever do. Everything's an essay. You can't even find a recipe online without somebody writing a narrative about it and why you should be interested in it. Here's a thought. I'm looking up a recipe online because I want to cook the damn meal. All right. Well, anyway, this one's a little iffy because the radicals look a little funky. But at pi over 6 or 11 pi over 6, you can see it's cosine comma sine. Every coordinate value in the unit circle is cosine comma sine of the given angle. And in both of these cases, whether it's pi over 6 or 11 pi over 6, the x value, which is the result for cosine, is equal to radical 3 over 2. All right, so this is actually a pretty decent one. I always go to the embeddedmath.com one for the blank ones whenever I want to give my students a quiz in my trig classes. So that's not really that bad. So maybe go there. But yeah, there's plenty of other options. But yeah. So anyway, just to get back to it, 1 over the radical 3 over 2 would give you that decimal. The radical 3 over 2. That's the 1.155-ish. Yeah. Unit circle. That's awesome. Yeah, I remember going to a wine tasting like 15 years ago. And the only thing I remember from the wine tasting, aside from okay, well, maybe I shouldn't go down that road, but I remember this dude was there and he had a tattoo on his arm, and the tattoo was that of the Pythagorean theorem, like a proof of the Pythagorean theorem. And I was like, I'm a math teacher, and even I don't think that's cool. I was like, that's lame, like it's not really like impressive on a mathematical front. Like, why would you get that tattooed on yourself? But I'm thinking, like, if somebody had a tattoo of the straight up unit circle on them, that would be impressive. Not because they're like advancing mathematical knowledge, but because they're like, you know what, this is so important that, I need it. I'm just going to get this tattooed on myself. I wouldn't do it because I memorized it, but if you have trouble memorizing, yeah, go ahead. Yeah, it sounds like fun. You're a tattoo kind of person. Just remember, if you get it on your back, you got to do it. You got to have them do it backwards, so that when you look in the mirror, you can. Anyway, that's the kind of thing I always thought to myself. If somebody rolled in with a tattoo of a solution to a problem on their arm, I'd be like, you know what? Go ahead. You sat in a chair to get that tattooed on yourself to answer a question on a test. By all means, use it. Like, what am I going to say to that? All right. So, first commitment. Right? I saw that in the chat, so it was like commitment. First derivative test. The first derivative test is an analytic approach for us to determine whether the critical value is going to yield a relative maximum or a relative minimum. All right, we can use the approaches that we were just talking about to determine extrema on an absolute level, but in terms of relative extrema, there was nothing about what we just did that would indicate that critical value was a turning point on the high side or a turning point on the low side, as in like a parabola facing upward. So we need something else to analytically take care of that for us. All right. And again, this goes back to what I was saying before. There's a lot of stuff that you have to take on faith, but I remember, and just this past spring in my Calc 3 class, I have students who always relied on just looking at a picture to find a maximum or a minimum. And then when it came time to do it in 3 dimensions and it wasn't quite so easy, they're like, oh, wait, how do you do that again? How does that first derivative test go again? So yeah, maybe you never end up there, but if you do, this is a technique that's going to be useful for you. And just nobody ever likes the sign chart. But it's kind of like a rite of passage. So we all have to do it. So it's saying, tell where the function is increasing, decreasing, and identify any relative extrema. Good news is this Desmos that I created and will share with you is going to be useful for that. All right. So find all critical values, break the interval into smaller intervals based on the critical values, points of discontinuity, and endpoints. All right. If there are any endpoints. Now you see in each of these cases, we're not, well, at least in the first two. The third one's kind of weird. But in the first 2 instances, I didn't restrict the domain. Right. So the way I would adjust my Desmos to handle that would be just put some really extreme value for A and B. Right. Just so I'm just gonna, you just typed in 0, dude. That's not extreme. No, just you want to see a pretty good look at the entire graph. So just put in something a little bit more extreme than what we had before. So in this case, I put in like -10 and 10. All right. But we'll come to that in a second. What we're going to do is find the derivative, of course, which would be 3x squared. We're going to set that equal to 0, and we're going to set that equal to 1/0. So 3, that's not what I wanted. 3x squared equals 0. This one is going to be irrelevant. because there's no instance in which my polynomial function could ever be undefined. So I'm going to divide out the 3, get x squared is equal to 0. And then I'll take the square root and you get x equals 0, and that's my critical value. All right. So we have a critical value, which is wonderful. We don't have any endpoints, but we got something. Let me get this original function in here because this looks kind of crazy. That secant function is extraordinary to look at. All right, but x cubed, x caret 3 plus 2. All right, so I have my original function and I have my derivative function. All right. There are no instances in which the function is undefined, the original function. So there's no discontinuities and we don't have any endpoints. All right. So what we do is we break this interval into the domain of the original function into smaller intervals based off of only the critical value, right? Not values, but value. All right. So the domain for this function, negative infinity to infinity. All right, this is polynomial functions everywhere continuous and it exists everywhere. All right, so what I do is I break up this interval based off of the critical value. So I'm going to say negative infinity to 0. Then we'll just look at the number 0 and then go from 0 to infinity. All right, these are the possible x values. We're going to make a little table out of this. All right, in the first row of the table, I'm going to evaluate f of x at each one of these x values, and then I'm going to draw a conclusion. All right. So the question is, what happened to the 3? There's a 0 on the right-hand side, so I just divided it out. Divided both sides by 3. Oh, you're correct. Yeah, cool. Okay. So now what I'm going to do is I'm going to look at my function and see, and there's a couple ways to do this. I'm going to look at my derivative function, I meant to say, on these individual intervals. I got an interval going from negative infinity to 0. And then I have an interval going from 0 to infinity. And then I also can evaluate it specifically at 0. But we already know what's going to happen to it at 0, at the x value of 0. We know that it's going to give us the derivative function equal to 0 because that's the approach we just took. We set the derivative function equal to 0 and solve for x. And that gave us the x value that led to the derivative being equal to 0. So we actually already know that this is going to be equal to 0. Right? It's just a question of, since we know that that's a critical value, so this is a critical value, it's just a question of whether it's going to be a relative max, a relative min, or maybe neither. Maybe it's just some kind of funky instance where, it's something other than that. However, looking at my graph could kind of steal your own thunder, I guess. You just kind of look at the original function and say, well, I already know the answer. I don't see a turning point at the x value of 0. So this is not going to be a relative max or a relative min. That's part and parcel with the approach of using Desmos or a TI calculator if you want. But yeah, we still need to know the analytic approach. Now, if you're using Desmos here, we have C values that represent critical values. Again, I can put 0 in, get to it. I just have to reset this to what it was before with the step being equal to 0. All right, so at 0, my derivative is equal to 0. Can't get it to stay on there, but there it is. But it's equal to 0, so we're good there. It's verified. But if you look at values less than 0. So between 0 and negative infinity, you look at the derivative f prime of c. Right, these aren't critical values, but these are just ordinary numbers being substituted into the original, I keep saying the original function, the derivative function. You can see that these numbers are all positive, right? And that's all we care about. This first derivative test involves creating what we call a sign chart that just designates the sign, not the numerical value, but the sign of the numerical value on certain intervals. So from negative infinity to 0, not including the 0, but from negative infinity to 0, all these numbers are positive, right? If you don't want to use Desmos, then what you would do is choose any number from this set. So any number from this set, plug it into the derivative function for x and see what you get as a result. Right? If you do that, just take note of what the sign is of your answer, and that's what goes in your sign chart. Right? And you would do the same thing over here. You know, you choose any number, plug it into the first derivative, and see what you get. Right? But you could also do it with Desmos and look at values that are greater than 0, and you see that all those are positive as well. All right. So we have all this information here related to the first derivative test, but let me just talk to you very quickly about what that means. All right. They're talking about sign changes indicating relative extrema. But if you look at it, you get two possibilities, really. And I'll just draw a quick sketch, nothing too elaborate. One that shows a relative max and one that shows a relative min. All right. So we have a relative max, also known as a local max. You'll see that sometimes. Relative min, also known as a local min. All right. So you'll see here that the slope is positive. All right. You're going uphill. Going into that relative maximum, the slope is positive. Coming out of that relative maximum, the slope is negative. Coming out of the relative minimum, the slope is back to being positive. So what we're looking at around a relative maximum is a positive slope transitioning to a negative slope. What we're looking at coming in and out of a relative minimum is a negative slope transitioning to a positive slope. All right. Those are your key indicators. If there's no sign change, then you're dealing with something that's not a relative extremum. All right. So if I get a plus sign, that means that the slope is positive, but it also means that the function is increasing. Increasing? I don't know. Increasing. No sign change means no relative extrema. Right? If you don't have a sign change, by definition, it's telling us that we don't have any relative extrema. Right? And you can look at the picture. I don't see a relative maximum or a minimum here. I don't see a clearly defined turning point. I see something that increases, levels off, and then continues increasing. I don't see something that increases, then turns around and starts decreasing. It's always increasing, or it levels off, but it never decreases. All right. So we would not say that there's a relative maximum or minimum here. Even though we get a critical value, it did not necessarily lead to a relative extremum. Now, that being said, if there was going to be a relative extremum, it must have been from a critical value. All right. So the only relative extrema in a graph, the only way that you would have one would be at a location of a critical value, right? That being said, not all critical values are relative extrema. All right, so let's look at another one. X plus 3 over x squared. So you see, you take the time here to type in your function the right way. And there's a little bit of a payoff in the sense that, you know, it's self-checking, where you go into the problem already knowing, all right, I have an idea of what's going to happen here. Now I just got to kind of make everything work out. All right. Like, for example, I see that this domain doesn't exist at all values of x. All right. There is a vertical asymptote at x equals 0. So my domain is everywhere but 0. All right. Then I got to find the derivative of this, which is fun, right? Because a little quotient rule action for you. I've done that in a little bit. So f prime of x low d high. That's my low. D high, derivative of x plus 3 is 1. Minus high, x plus 3. D low, which is your 2x. Over denominator squared. Square that x squared, you get x to the 4th. Now, in the previous unit, when we were finding derivatives, we didn't have to simplify because it didn't serve a purpose. Now it serves a purpose because we have to solve here in order to find critical values. So I'm going to clean it up a little bit. X squared minus 2x squared plus 6x over x to the 4th. So f prime of x is going to be negative 2x squared. I'm sorry, negative x squared, apologies. Plus 6x over x to the 4th. I'm noticing a common factor up top that can be pulled out. Pull out that x. When I pull out that x, I can cancel it with one of the x's on the bottom. And then we can start getting into the part of the process where we find critical values, because f prime of x is equal to negative x. Well, that's just great. Oh, we got to it quickly. Quickly being the word of the day. We'll let quickly is the word of the day. So we're going to take that derivative and set it equal to 0, set it equal to 1 over 0. And in this case, we could do both. So I'm going to have negative x plus 6 over x cubed is equal to 0. Negative x plus 6 over x cubed is equal to 1 over 0. And you go through the process of solving for both. When you cross multiply here, you get negative x plus 6 is equal to 0. Add x to both sides, you get x equals 6, nice critical value. All right, when you cross multiply over here, you get x cubed is equal to 0. Solving, you get x equals 0. Now you might look at that and say critical value, but we have a vertical asymptote at x equals 0, which means that that can't be a critical value because there's no graph there, right? Location of the vertical asymptote, right? There's no function there. So it can't be a critical value because it doesn't exist as part of the function, right? It has to be part of the original function in order to be a critical value on the function, right? I'm going to steal some space. I was about to try to resize the living daylights out of this, but I'm going to steal some space below and I'll take that as a typo, the spacing. So I'm going to make a table out of this. Oh, and let me actually keep this zoomed out for a second. The first step in the process, find all critical numbers on the interval, but then break the interval into smaller intervals using these critical values, points of discontinuity, and the endpoints. We still don't have any endpoints, but we do have a point of discontinuity, that x equals 0. So even though the x equals 0 is not a critical value, it still becomes an important part of the table, all right? So I'm going to break up my domain, which goes from negative infinity to infinity. I'm going to break up that domain to go from negative infinity to 0. We'll stop at 0. That's the vertical asymptote. Go from 0 to 6. We'll stop at 6. That's our critical value. And then go from 6 to infinity. That'll be our set of x values. Oh, that's weird. All right, so we'll evaluate our original function at each one of these locations, and we'll draw some conclusions. All right. And again, the good thing is we have Desmos to help us do this because I just use the same little applet here and just focus on values of c that are less than 0. So any of these values between negative infinity and 0. All right. Sorry, I'm just double checking something. Son of a gun hack. Very small error, but even I'm capable of making this mistake. There was a negative here. When you distribute a negative, fun fact, you reverse the signs. This guy over here should have been negative. Nothing like what we call a cascading mistake. Carries all the way through to this final part of the process. All the way through. Gotta love it. I'll zoom back out in a second so you can look at the scope of the grand scope of this blunder. I was looking at it and then comparing it to the graph. I was like, wait a minute, you're going to be on the wrong side. I'll show you in a sec. Almost there. Brutal. And just wait, folks. You're going to love what's about to happen next. Every one of those yellow highlights was a mistake, which means the whole sign chart needs to change. should have been from negative infinity to -6. You have to go in increasing order. This would be my critical value. And from -6 to 0, there's my vertical asymptote. That's what it should have been. Apologies for that. It's just when I looked at the graph, I was like, wait a minute, there's no turning point at 6. Now, there doesn't have to be, but I see one at -6. It's ever so slight, but the more you look in, the more you see that it drops down, and then it starts to possibly, maybe not definitely, but it starts to possibly come back up on itself, right? So I'm looking at this and I'm like, if there's going to be a turning point, it's going to be over here, not over here. And I'm just thinking to myself, why on earth do I have a +6 as a critical value? And then I saw it, plain as day. Also, I wasn't getting the sign change that I was looking for in this, because going from negative infinity, if you will, to 0, we got our undefined at 0, which is fine. But then we got these values that all look pretty good. All right, they're all positive. But then as you scroll past -6, you see that they all start becoming negative. I expected them all to be positive over that interval if that asymptote was correct. So negative, then once you hit 6, they become positive. So in fact, we can start labeling that. So they're negative, means it's decreasing. We know it's going to be 0 here. Then once it hits 6 on the interval of 6 to 0, they start becoming positive. So that's increasing. Then at 0, it's undefined, but we knew that. I could write it as 1/0, or I could just write in undefined. But we knew that because that's the vertical asymptote. That's nothing new. We knew that going in. All right, but then after 0, you see that it's always negative from there on out. And that's actually a good way to verify, or at least start thinking towards things like asymptotes and end behavior, right? But that's a different conversation for a different day. So it's decreasing. So in this case, we have something that is going down, then so going down, followed by going up. The transition being the location of the critical value. So this would be a relative minimum. Right, so this one has a relative minimum and a vertical asymptote. Right, now you see here, it starts off decreasing, followed by increasing. So you might look at that and say, oh, look, sign change, that's great. You know, it goes from decreasing to increasing. And then you say, oh, wait a minute, what about where it goes from increasing to decreasing? Wouldn't that be the same thing? It would, except for the presence of the vertical asymptote. Because there's a vertical asymptote there, there's no graph. So there's no transition. Now, if this graph increased and then turned around at the top, came back down the other way, then it certainly would be a relative maximum. But that's not what happens, because there's a break in the graph. It's discontinuous at that location, right? The sign chart is actually your answer. So you don't need to do anything more than that, because the questions here are asking you to identify instances in which the graph is increasing, decreasing, and then also identify any extrema, any relative extrema. So the table has everything you need. I've shown the intervals where it's increasing and decreasing. And by labeling this as a relative minimum, I've identified any relative extrema. So mission accomplished. All right. So I'm going to put a star on the next one. And because of my blunder, we'll end it here, because I wanted to get into the second derivative test, but I don't want to rush it. So we'll pick that up next time. So I'm going to stop the recording.